Great, so today we're going to talk about the Unit 1 exam. And first I'll talk about some exam studying strategies that might help for this exam. Then we'll go over some of the homeworks and kind of just talk about the overall concepts for this unit. So I would say a strategy for studying for this exam is to make sure you understand what was going on in the homework assignments. We'll talk about those in a second. Look back at any quizzes and vocab from either lecture handouts. Some of the lectures had handouts. Didn't get a chance to print them out for you, but they are posted on Canvas. So check those out for particular weeks. For example, there's one for snow, there's one for ET. Make sure you understand the big concepts from the readings and from our lectures. We'll talk about these big concepts in this list. And that might mean leafing through the readings again and making sure you understand the kind of the vocab words, definitions, that sort of thing. If you take notes, we didn't talk about that at the beginning of class, but if you take notes, review your notes to go back and identify those concepts and refresh your memory. And then finally make a crib sheet. I have people who take exams with me make a crib sheet. I think I've had all of you before. So at least one-sided, handwritten, that you bring to the exam, and then you turn in with the exam. I'll give it back to you. I think crib sheets are great study tools. They kind of help you organize your thoughts and writing down important equations and stuff like that.
So on a crib sheet, like we no like problems, but just we can write definitions and equations.
You can write whatever you want on it.
Oh, okay.
Yeah.
How many? Or is it just one page?
You can do two-sided. I mean, you can have as many sheets as you want. Just at least has to be one-sided.
So we're gonna have 3 pages?
I don't know. Like I guess I've always said two-sided. Honestly, I think like in case, yeah, let's do one sheet front and back. How's that sound? Because then, like, well, I don't know, find old exams and just start writing them down, and we don't necessarily want to do that. But yeah, you're welcome to write out problems, equations, that sort of thing. Just bring like this is not the PE where you bring in like your suitcase of books and stuff like that.
Okay, let us use the textbook and bring whatever as much notes as we want.
Yeah.
So I printed out every PowerPoint she went over.
Yeah.
I was like, can't test us on any more than what she talked about. So
yeah, I think what you run into there potentially is people not necessarily studying and just say, oh, I'll figure it out on the fly, and that's not going to work.
that's
Yeah.
trying to find something through all that.
It's not going to work. So
I found it to not be as useful as I thought.
yeah. So I don't want to give you a false sense of security by like bringing a whole notebook in and not studying. So we have exam 1 resource book. I'll print this out. You're welcome to look at it. You're welcome to print it out yourself. I'll probably update this before the exam just so you know, but there's a lot of information here, how to basic watershed water balance, how to delineate a watershed, energy balance, frequency analysis, recurrence interval, AEP, risk analysis, precipitation analysis, and then evapotranspiration. So there's that energy in the mass balance or water balance methods. And I try to be pretty, I don't just give you the equation, I walk you through a lot of stuff and define all those terms.
This is something we'll have on the
Yep. And it has units, right? Tables, conversions. What?
No, I feel like that's like it looks like we did.
Yeah, it's a lot. Yeah. It's like it's not a mini textbook, but it's like a lot. It's like some lecture notes, basically, distilled.
reading straight through that be a good study tool, do you think?
Be a great study tool. Yeah, absolutely. So that's under modules. That's under the first first module. Course information. All right, let's get this whiteboard running. Let's see if we got it. Yes.
I saw an article that said, I didn't have time to read through it at the time, but it said La Nina, that's in Colorado.
Well,
So
yeah,
how do they know that, and like where are they seeing that from?
let's take a look.
Where's the problem, right?
No, I thought La Nina,
That's the.
yeah.
So what is La Nina versus El Nino?
That's when we get all the cold water near the South America Pacific, right?
Mm-hmm. So it's the sea surface. So it's called El Nino Southern. Is it Southern Oscillation? No. Let's see here. El Nino. Okay, so what this is a presentation that NOAA puts out. They do it every, I don't know, month, every few weeks. And they analyze the sea surface temperatures, sea surface temperature anomalies, so departure from normal in a given season. That's a weird graph. But they look at these different zones. You can see these zones across the equator in the Pacific Ocean. And they look at sea surface temperatures there. They have buoys, they have satellite monitors, and they'll tell you if it's colder or warmer. And so you can see that it's colder here than normal, which means La Nina. If it's warmer than normal, it means El Nino.
So the La Nina, since that's in Colorado, is that a good sign or a bad sign?
Typically, it means that we're going to have a drier year. If you look at, I think I showed you guys a box plot. And typically that box plot, the interquartile range, the middle 50% of observations of, I think, snowpack basically are below average for La Nina years. Yeah.
I didn't know if when I saw that, I didn't know if I should be excited or not. But
Yeah.
Farmer's Almanac said that winter's supposed to come late, but we're going to have a pretty good spring.
Okay.
So,
Let's look at the last two homeworks.
I feel like Noah's probably a better resource than Farmer's Almanac.
I'm going to go ahead and say that's probably right.
That one, wait, where it said La Nina?
No, the one like gave you on the
Oh, the Farmer's Almanac?
I kind of wish NOAA would do their own Farmer's Almanac. Maybe they do, but like publish it that way. So it's like, okay, we got, the sea surface temperatures. We like actually have data that can predict long-term. That would be great. I mean, I'm not saying Farmer's Almanac doesn't do that. I don't know what their methods are, but let's talk about this problem. I think you guys mostly got it. I asked you to take this probabilistic risk equation and invert it. So real quick, to invert that equation, we start with, all right, let's see how this goes. So we have P is equal to 1 minus 1 minus, oh, wait, it's R, we're doing R. This is the, R is equal to 1 minus P to the N. Did I get that right? Yeah, okay. And then to invert this in the homework, you basically bring all your like terms together, or bring all the terms together and then raise it to the 1 over n. So in this case, we get P is equal to 1 minus R to the 1 over n. And who can define what P is here? I guess Christian, will start with you. Yeah, probability of exceedance, or AEP. different ways of writing that. And this is related to our design event. And this is chosen by, definitely go look back at the different ways we approach design hydrology. That was our second lecture. And there's a reading that kind of gives you a rundown. So how do we choose it? Well, it's kind of risk-based, right? There's standards, there's guidelines, there's different approaches. But ultimately, we need to choose a number, and that number has a probability, which is an annual exceedance probability. So this is the 1% annual exceedance probability event, which has some sort of, rainfall depth or peak discharge associated with it, right? We choose a probability, we can go back to the record and figure out what that actual rainfall depth and peak discharge should be. If we calculate risk, what are we actually calculating? If we calculate R, Val? We plug in a P, we plug in an N for years.
The probability that it happens in one given year.
So probability is P is the probability that will happen in a given year. And then if we throw in P, we throw in N, which is the number of years. I should have defined that first. Design life, right? How long we expect this infrastructure to last, or the period that we're interested in. So if I choose a P and I choose an N, I calculate R. What is R telling us?
The chance of it happening over time.
Exactly. So R is equal to the probability of events. It's a double probability here, right? Of an event with probability P occurring over n years. Great. And so this is what we call probabilistic risk. And it tells us the probability that this event associated that has this annual exceedance probability will occur over so many years. And so I can say, okay, I have a bridge. I expect this bridge to be around for 100 years. I've designed it to accommodate the 100-year flood event or the 1% annual chance flood event. So P is equal to 0.01, N is equal to 100 years. What's the risk of this overtopping over this 100 years? And I think, I'm just going to guess, I think that's about 1.64. Three, 3.63. All right, we're close. We were close. 0.63. And honestly, if you plug in anything, if you plug in 0.02, and then you plug in 50 years, you'll get the same number. So this is kind of like the asymptote. Well, it's not. Sorry, it's not an asymptote, but for the probability that an event of the same return period will happen over the same amount of years is going to be 0.63. But certainly you could imagine a situation where you have a much lower probability in a shorter time frame or something like that, and the risk would be zero, would be different. If you invert this then, what information am I getting with this inverted equation here, Jake?
Occurrence interval that you will give you a certain amount of risk over.
Yeah, so you set your risk. Set your N, and then you calculate P, which is your AEP, your annual chance. So this is your design event. So what's my risk tolerance? Is it high? Is it low? And then given based on my risk tolerance, what event should I design to? Definitely an important concept. There's definitely going to be a question on the exam about this. The probability, the risk that we'll ask you about this over 10 pages of an exam, 100%. All right. I don't know. I just came up with a number. Can we clear this? Let's see. Is there a mass erase? Clear canvas. There we go. Okay. Any questions about these? Low risk, high risk, right? I think you guys got the concept. If you have a major infrastructure, maybe your risk tolerance for failure is probably going to be less than a culvert over a small road or under a small road or something like that. Okay, this, obviously it was challenging dealing with the data. I'm not going to have you download and deal with data on an exam, but I might give you data, right? And I might have you walk through, say I give you an annual maximum series, the first 7 rows or something like that. It's already sorted for you. And I have you calculate this probability of exceedance based on the Whiteboard plotting position. I guess I should ask, did you guys understand that concept? I know there's a lot of issues with the data analysis, but the probability of exceedance problem. So maybe we can open up, let's open up, let's see if I have a spreadsheet handy. Oh, I'm in the wrong class, thank you. That is not what that folder looks like. I was gonna see if we could pull that up, but I'll just write it, I'll write it on this. We'll do an Excel, that's what we'll do. So, boom, it'll be easy. Okay, so if I give you, an annual maximum series, what is an annual maximum series, Edgar? So if we do precipitation, we'll define a duration. So define duration. So in this case, we did 24 hours, right? And then, so if I define the duration, then what is the annual maximum series for the 24-hour rainfall event? Yeah. So in a given year, maximum depth that fell at this gauge over a 24-hour period. Okay. And it was based on day, right? So that's not a perfect data set because you could have a storm that goes into the next day. So whatever. It wasn't a perfect data set, but it's something. Okay, so annual maximum series. Each year we have one value. And so we'll just say 24-hour rainfall depth. So say I'm just going to make a gauge up. This is the gauge at Walker Airport. And so this is our depth in inches. And then we're going to do rank. And then we'll do probability of exceedance. All right, so I'll just put some numbers in here, 1.25. Oh. We'll do rank 1, 2, 3, 4, 5, and then we'll jump down dot, 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 dot to 0.25, 0.22. And this will be 120.119. So we have a record of 120 years. I want to calculate my probability of exceedance. I'm just going to do the Whiteboard plotting position. And so in this case, what does n equal to? 120, so this is the number of years we have on record. And then it's m over n plus 1. That's the Whiteboard plotting position. It calculates our probability of exceedance. So that's going to equal rank divided by n plus 1. And so I calculate my probability of exceedance. We'll just make this a percentage, a little easier to read. And then I could also calculate the recurrence interval, which would be in years. Does anyone remember how to calculate that? Yep. So just the reciprocal of our probability of exceedance, and that gives us the recurrence interval of this storm events in years. And Dylan, can you define what a recurrence interval is?
It's like a timeline that said that each event saying that this event could, like for the first one, it could reoccur in 121 years after it occurred again. But it's probability faster.
So close. And that kind of gets at why we try to use probability of exceedance, which is interchangeable with annual exceedance probability. Because what this really means is, on average, if we had, say, 10,000 years of record and the climate wasn't changing over 10,000 years, then we would expect to see a rainfall event of this magnitude once every 121 years. So that's an average recurrence interval. But often people misinterpret it and say, well, oh, it's a 121-year recurrence interval. We had this event happen 10 years ago, so we don't expect it to happen again for another 110 years. If you had 10,000 years to sit through, you would see it happen on average once every 121 years, but in reality, your annual chance of seeing that storm is about 1%, a little less than 1%. Complicated, but this ultimately gets at the probability.
You would see it not over 10,000 years, it wouldn't be like 121 years where like clockwork, you could just like say, you would see it this many times in those 10,000 years.
Yeah. So if I were to say 10,000 divided by 120, right? That's how many times I would expect to see that storm. Yeah, I think that's a good way of thinking about it. Yeah. And if we get back to statistics, we could get into the actual derivation of this, but so that's what we're doing here. We're not, so the values themselves really don't matter. They're not part of the calculation. It's just the order of the values. And so we're basing this frequency analysis is based off of just this record, and we order that record. Now remember that the partial duration series, what's the difference between partial duration and annual maximum, Jake?
Partial duration gives you any storm that exceeded a certain value over your time period.
So you set an arbitrary threshold, and instead of taking the maximum each year, you take anything that occurred over that threshold. So you end up with more data. And the key thing to remember with partial duration series, let's go back to our whiteboard. If I do this, we'll do probability of exceedance, and we'll do 1% here, and we'll do 100% here, or 99.999, you know, and then we'll do rainfall depth. So we have really high and then it kind of comes down, something like that. If this would be our annual maximum series, AMS. And then we could do a partial duration series. And what that's usually going to look like is this. Let me just erase that, sorry. It basically converges, at least theoretically, around the 10% event. So for these smaller storms, you're getting a lot more information. But once you get to less frequent, bigger storms, these two series converge. So understand frequency analysis, understand how to read those curves, those intensity, duration, frequency curves. We can take a look at that in a second. Okay, I think that's all I'll say for this, unless there's other questions. We can take a look at these intensity, duration, frequency curves and just understand how to interpret them. Here we go. Okay. So this is one's from a partial duration series. Depth, duration, frequency. So depth is just inches, it's not intensity here. We've got duration on the bottom on the x-axis. And then we've got average recurrence interval for these curves. So what do we see here? We've got different durations. We've got an increase in depth as you increase the recurrence interval or reduce the annual exceedance probability. If we look at this one, this is recurrence interval on the x-axis and then duration on the y-axis. And obviously, the longer duration, the more precipitation we would expect, right? We could also use equations to create those. You guys saw an example of that. Any questions about homework 2 before we move on to homework 3? I will say this, when you're comparing Grand Junction to Denver, this gets at kind of how, what I'll call a flood climatology. Floods we typically think of as weather, right? You get a big storm event, you get a big dump of rainfall. But we know that on average, Denver gets more extreme flood events, the Front Range does, right? And why is that? Well, orographic effect, you've got mountains, you've got, in the summertime monsoon season, there's more precipitation that can fall out, more moisture that's brought against the Front Range, which can then hit the mountains and then fall out as big storm events. Grand Junction has mountains, right, but not necessarily the Front Range, they're a little farther away. And certainly we get big storm events that can happen on the Book Cliffs or the monument around us. So we do have this kind of smaller scale orographic effect, but a lot of that moisture is going to pass over us and hit the Rockies, hit Vail and Aspen and these higher areas. So they're more likely to get more rainfall because of that orographic effect. Okay, let's look at homework 2, and then we'll kind of do a more general review. Or sorry, homework 3. And I'll just talk about the first 2 sections, because we're not going to talk about soil moisture on the exam.
Soil moisture.
Correct. Yeah.
Will it be on the next exam then?
Yeah. I will. Soil moisture. So the soil moisture part of this homework will not be on the exam. All right. Let's see. How about I'll just bring up the solution? I think that'll probably be the easiest.
Are these posted on Canvas? Resolution?
No, I graded your guys's, so I can talk about these solutions. And if you want to come follow up on any questions with me, you're welcome to. Where there were errors, I try to give you the answer. So take a look at that. Okay, so what do we look at? We have this data I gave you, and we had snow depth, which is the blue one. We had snow density, which is purple. And then we had SWE, which is this dark blue right here, and then cumulative precipitation, which is the orange. And how'd you guys interpret this? I love giving graphs and having you interpret things. So I think everyone got this pretty well. You know, we had depth, snow depth kind of peak in January, and then that snowpack compacts, right, over time. We're getting more snow, right? You can see it's kind of coming up, but it's compacting, and it's sinking on its own weight. It's also, you're getting warmer days, and so it's kind of melting a little bit and compacting as it goes. So that's why you see this increase in density signature right here. And then our peak SWE actually occurs right here. You get this peak in early April. And we're not at peak density yet, but we are at peak SWE. And that makes sense. Like, you can still have a higher density, but you have overall less snowpack, right? At the very end of the snow season, everything is kind of basically like mashed potatoes. It's super heavy. You probably shoveled it before. That's the densest kind of snow at the end of the season. Now everything drops sharply and everything melts off pretty quickly, right? And you've got this melt off period. You can see that the SWE is slowly reducing over time. The density goes to 0 right as the snowpack goes away. And then we compared SWE in blue with runoff in green. And you can see that you've got some early peaks in runoff. We didn't have temperature here. Temperature probably would be helpful, but probably had a spike in temperature, get a little bit of runoff, things cool down, and then things heat up again. You can see where SWE is decreasing. That's where we get runoff. So where did that SWE go? Well, it melted, right? That's snow water equivalent. And then now we've got the big melt off period, and that's where we get our peak and discharge. When things are melting off, we haven't talked about runoff yet, but just conceptually, a lot of that runoff is going to go quickly into the streams. A lot of it's going to also infiltrate into the soil. And that's where you get, the snow is gone, right? But you still have this runoff signature. These little peaks are happening from rain events, right? We don't have snow in July necessarily, but we'll get rain events in the mountains. And so you certainly have rain influence on the hydrograph, but a lot of this is this, as the groundwater reservoir drains from all this snow that infiltrated, you get this recession.
That was one of the questions that I was not able to answer. I didn't really know how to interpret them on that homework. Was when you asked how much was rain and how much was snow.
Yeah.
And from that, it was just.
So how did you calculate that? I said use peak SWE for your snow, right?
Right.
And so that was about 19 inches. How do you figure out your rainfall? So let's see. Let's see. Do we accumulate SWE? Do we? So the way I did this is I gave you cumulative precipitation, and you can actually accumulate SWE, right? So as you go along, you can say, okay, we have up into the peak, basically, we've had this much snow fall up to this point. So I could show, this is kind of like this version of SWE just shows you what's on the ground. And what it doesn't show you is what's fallen all the way up to, the season, all the way through the season, right? That's what this cumulative rainfall shows you. And so what you could do, what I did here is I just did, okay, SWE, I made a new column called SWE accumulation. And I said if our SWE from the existing day minus the SWE from the day before is less than 0, then we didn't get any new SWE. But if it is greater than 0, then give me that daily increase. And so you accumulate SWE, and then you ultimately end up with about 24 inches of cumulative snow water equivalent versus about 30 inches of precipitation. Oh, of total precipitation. Does that make sense? So what you have to kind of interpret it, and maybe I could give you guys a little more hints on this, but the idea is this is cumulative total precipitation, which includes rain and snow. You can see it still increases after the snow starts melting, but it matches the snow right here, right? And you can see as it departs, what's happening is there's a one-to-one relationship with SWE and cumulative precipitation until at some point you start to get a little melting in the season or a snow ablation. So we're losing water from it, but this record of cumulative precipitation, it keeps tracking the fact that that snow has fallen. I won't give you a problem like this. That's a little, you got to think a little bit more about that one and use Excel, right? So what I ended up with is I got a cumulative SWE was 24 inches, peak SWE was 19. So what that means is there's a 5 centimeter difference or inch difference between the peak SWE and the total SWE that fell out of the sky. Does that make sense? It either melted or it sublimated before you got to this point. And then I said compare volumes. So you can convert a flow record to a volume record by just multiplying by the time. So the average daily discharge, I'll just write this down on the whiteboard. So there's definitely gonna be a lot of conversions, and we'll talk about evapotranspiration in a second. Say, for example, I tell you that the average discharge coming out of a basin over the snowmelt period is equal to 20 CFS. And I want to compare that to a peak SWE of 19 inches. So I'm just making these numbers up. Well, I got this one from our problem. Who can walk me through how to get this CFS to inches so I can compare the runoff with the SWE? I need an area, exactly. So this is a volume over time. And to get from volume to depth, right, this is depth, I need to divide it by area. So volume over area is equal to depth. And what area would that be? Watershed area. So we have a basin, and we have 20 CFS coming out of it on average over, say, 365 days. And so to do this, I would say Q, which is in cubic feet per second, times, is it 86,400 seconds per day? Okay, times 365 days. And then that'll get me a volume. That'll give me cubic feet over a year, right? So now I need to get it into inches. So how many cubic feet per inch? So that's 12 times 12 times 12. I don't know what that is. It's okay, we don't need to actually do that, but we can just say, so 1 cubic foot times 12 cubed inches. So now I'm in cubic inches, that's a really big number. And then I'm going to, so now I've got my volume in cubic inches. Now I need to divide by area in inches squared. Is this the best way to do it? Not necessarily, because you get really big numbers when you're converting a watershed area into inches. But if this is my heart-shaped watershed and it's 10 square miles, then I want to do square miles into square inches. So now I'll end up with a depth in inches that is related to this runoff. So this runoff volume that now is in a depth. And I can compare that directly with peak SWE. So if I say, if my peak SWE is 19 inches and my runoff depth is 16 inches, then I can say, what's the water yield for this basin? Is equal to, in this case, the total runoff. So we'll just do runoff over peak SWE. And in this case, it was 16 inches over 19 inches, which is, I don't know, 85% or something like that. 84%. Hey, not bad. 84%. And the idea here is you had, at the peak, you had 19 inches of SWE that was in the basin, and you ended up with 16 inches that ran off based on that average discharge. So 84% of that water ran off. The rest was evapotranspired or went into long-term groundwater storage, something like that. So that's a basic unit conversion. We also did a lot of this when it came to the evapotranspiration problems. Let's take a 3-minute break, and then we can jump into that stuff. But I'll take any questions too if you guys have any.
You can ask us about like the steps of
So Edgar asked about economic risk, and it's a bit of a loose definition. There's a lot of ways to define economic risk, but in this case, we're going to call it we'll call it R econ. I don't think there's necessarily a good symbol for this, but does anyone remember how we define that?
it's probability cost.
Yeah, probability times consequence. And you could talk about, you could enumerate consequence a number of ways, but the easiest way is just the cost.
So that probability is the probability of risk, right? It's not the annual probability.
Yeah, so you could think of it a number of ways. So you could say, what is my economic risk in a given year? So in a given year, and that would be our little p times the cost, right? In a given year, the chance of something happening, the probability of exceedance of your events is going to be p. So 1% AP, your probability in a given year of that happening is 1%, or something worse happening is 1%.
Your economic risk would be 1 times how much project costs, which is your cost once, say 5,000.
So it would be the probability, so your annual economic risk in that case, if P is equal to 0.01, and then in this case, we would get our R econ is equal to 0.01 times 100K. And that would be in a given year. That's your economic risk. But often we're thinking about this over a longer period of time. And so if we think about the project like design life, then yeah, Edgar, I think this is what you're getting at. Then we want to put in R that we calculated earlier, that probabilistic risk. So R econ is equal to R times consequence. In this case, we have n years, and then we have whatever that p value is, right? So this is the probability of that event occurring over so many years, given that probability of the event times the cost. So you might think of a problem here, an economic cost problem, saying, all right, what is the economic risk of I-70 shutting down from a fire, right? Then we can look at what's the probability of a fire occurring that shuts the highway down over say 50 years. And maybe we're looking at some sort of like fire mitigation program. All right, I bet you this is a conversation that people are literally having right now at CDOT. They're like, how the heck can we keep Glenwood Canyon from burning again? Well, maybe the whole thing burned and there's no fuel left, but somewhere else, from a fire that starts, say, from a spark or someone throwing a cigarette out the window. Okay, well, what do we need to do? Get rid of all the grass, or maybe like mow it more or something like that, so it just can't catch on fire. And what's the cost of that program? Well, that could cost us $500,000 a year to do that program. All right, so we add that up over 50 years, do an annualized cost or something like that, and then look at the risk of that fire occurring over 50 years, given the probability of fire. And then we can calculate, and then we also know what the cost is of shutting I-70 down. Well, let's look at, it was shut down for almost 3 weeks or something like that. What is it? We can do a study on the economic cost of that, okay? Of the detour and the tourist economy and all these things. So we've got that consequence then. We've got that cost, or we've got the probability of that event occurring over 50 years, and then we can compare that to that mitigation program. Is it cost effective? Or do we just say, well, it's not, it's too expensive, so we'll just, take the risk, we'll assume the risk. So that's how you might think about that. So annual economic risk or over to the design life. Let's look at some evaporation problems right quick. Okay, so we have this, we'll do a water balance one. All right, I said we had a farm plot. It was 500 acres. And I'm just going to make some numbers up. Some of these are probably what the problem was. So we irrigated with 1,000 acre feet of water. And we'll remember that an acre foot is 1 foot of water over 1 acre. That's an acre foot. It's a US way of measuring water when it comes to like big amounts of water reservoirs and irrigation and all that stuff. So 1 acre foot of irrigation, we had 200 acre feet runoff the property in the irrigation ditch. And then we had over the growing season, I think we'll just make a number up, 6 inches of rain. And so I said calculate ET. Now you don't necessarily have to go back to that whole big drawn out equation, right? Oh yeah, that was the other thing I threw this in. I said the soil moisture. It started out at 2 inches per foot and it ended up as 1 inch per foot. And what is the soil moisture term in our water balance equation? If my water balance, delta S, yeah, so delta S is going to be equal to our inputs minus our outputs. So our inputs are our precip, our irrigation, and anything else coming in? I think that's it. Our outputs are runoff and ET. So what's a good strategy for solving this kind of water balance equation? Yes, everything in the same units. It could be acre feet, it could be inches. I would use one of those. So in this case, let's do acre feet. All right, so our delta S term is 1 inch per foot. So I need to convert that to acre feet. If I have a 500 acre farm, then I would just do, so 1 inch per foot. And I'll just treat this as 1 inch. And we need to convert that to feet. So I'll divide by 12. And then I'll multiply that by 500 acres to get acre feet. So now we have delta S in acre feet. Our precip, I can do the same. So 6 inches fell over 500 acres. So I get precip in acre feet. Irrigation is already in acre feet. Runoff is in acre feet. And then I just need to calculate ET. So I said calculate ET. I can rearrange and solve. We'll do precip plus irrigation minus runoff minus delta S. And maybe I say, give me ET in inches. And so now we just need to go from acre feet, and it really just is acre times feet. So to get from acre feet to inches, I will divide by acres and multiply by 12 inches per 1 foot. So gets acres out, gets feet out, I'm left with inches. Make sense?
So the part that confused me on this problem was the delta S.
Mm-hmm.
So they're going like inch per feet.
Yeah.
How do you just get that into feet? You just
Yeah, I think there might have been another piece of information that would have been helpful, which is to say we only care about the first. Assume that our control volume is only that first foot of soil.
so we don't shut that one inch.
Right. So you would just say, okay, anything that fall. I guess that would be an important statement to say is like anything that goes below a foot, soil moisture is assumed to go in the runoff. That would be an assumption we have to make.
Delta S negative.
Did I do that? Let's see. Delta S, change in source. Yeah, so delta S is negative.
It's never from 2 to 1.
But I guess if you were to,
So you're losing soil moisture.
yeah. So if you were to write all this out, right, ET is equal to all this stuff, it's minus delta S, but in this case, to solve for ET, whatever you put in for delta S, in this case, it'll be a negative number, so you'll end up adding it.
Why is it
Because this was S1 and this was S2. Yeah. Okay, so it's just a lot of conversions, and getting everything in the same units is the key strategy here. Let's do an energy balance one. Yeah. Okay, so let's do this. Okay, so for the energy balance so for the energy balance version of evapotranspiration equations, we say that E naught, which is potential evaporation, basically given an unlimited water supply, is equal to K plus L, and these are, this is shortwave and long wave radiation. So this is the energy coming into the system from the sun. Short wave, long wave. And we're going to divide that by the density of water, the heat of vaporization of water. Remember, it's that big number in joules. And this Bowen number, 1 plus Bowen. This Bowen ratio. This is like, the Bowen ratio is a key definition to know. Does anyone remember what it is?
the rate of evaporation? Like in the west, or in the
That's the Pan coefficient. The Bowen ratio is, let's see if I got it written down here. I don't want to get the ratio wrong. It is the, So what it is, it's the ratio of sensible heat leaving a system. Remember, you absorb radiation and then you heat up and you release heat via infrared radiation. So sensible heat flux over latent heat flux. And latent heat flux is the energy leaving the system in water vapor, the stuff that's actually evapotranspired. So if I give you a Bowen ratio as 0.5, that means well, so what it means is that the sensible heat flux is half of the latent heat flux. So there's more energy leaving the system via water vapor than long wave radiation, infrared radiation.
It's never going to be above 1.
Yeah, I think it could be above 1, certainly. Yeah. When you have water limited conditions, like really dry soil. Yeah. In which case, if it's above 1, because it's in the denominator, it's going to reduce the potential evaporation, right? What this tells you essentially is how much water vapor is available for evaporation. If it's a really big number, there's not a lot of water available. If it's a low number, there's a lot of water available. And because it's in the denominator, that'll increase our potential evapotranspiration. So yeah, if you're out on a parking lot, asphalt, super hot, not a lot of soil, not a lot of moisture, not a lot of wet soil available, or maybe you're out in the desert over by the Book Cliffs and it hasn't rained in a while, you're going to be feeling that heat coming off the soil. That means you have a high Bowen ratio, a value greater than 1. If you're sitting out there on the grass on campus that's been irrigated really well, and you've got the sun out, you feel that humidity coming off the grass, that's a low Bowen ratio. You're having a lot of evapotranspiration happening. Okay, so in this case, I give you a bunch of different values. So I give you K is equal to 200 watts per meter squared. Long wave radiation, 50 watts per meter squared. I give you Bowen ratio 0.5. And then it says use this energy equation to calculate evaporation for a lake over the course of a day in centimeters. Make sure you follow the units. All right. So everything's probably going to be in meters, right? And you already showed that this is length per time by the units. And so you should get a value that's length per time. So I'll plug in 200 watts per meter squared plus 50 watts per meter squared all over the density of water. So we'll just do 1,000 kilograms per meter cubed times the latent heat of vaporization. Let's see if I've got that handy. Oh, there it is, 2,260 kilojoules per kilogram times 1 plus Bowen, which is non-dimensional. Okay, well, I'm not going to go between watts and kilojoules. Is that just, is it one? Okay. But we'll trust that these units work out. And so ultimately we can calculate this and just do that real quick. 250 divided by that's kilojoules, so we'll make sure we get we multiply that by 1,000, right? Okay, and that's going to be in meters per day. It's a really tiny number. That's meters per second. Thank you. Okay, so that's going to give us. Let's do it in scientific. Meters per second. And then we're going to go to meters per day. So we're going to times that by, let's see. Okay, times 100 times 86,400. And I get 0.64 centimeters per day. Is that what y'all got? Okay.
I don't remember where I got my latent heat evaporation.
2.5.
I did 2.5, yeah, megajoules per.
Yeah, that's fine. That's close enough. I didn't, if I took any points off for that, let me know. I don't think I did. Yeah, I remember a bunch of people got like 0.58 or something like that. So,
I don't remember where I got that.
It was in one of the lectures. It was in one of the notes you guys.
okay, yeah. That's going to vary based on the temperature of the water, right? So, whatever condition that is. That is how that works. And we are just about out of time. Take a look at the resource book, and I will also post this. This is just kind of the major topics from each section. So I'll post this on Canvas as well. Take a look at it. We'll have, I don't know, maybe 4 to 6 conceptual questions, short answer kind of questions. And we'll have a handful of calculations, but be prepared to like read a chart, right? Like design hydrology, know how to go from an intensity, duration, frequency curve, from a point depth to an area depth, right? Kind of go through those steps. The design hydrology steps. Let's see here. Yeah, so say I give you a frequency and a duration, go to an IDF curve and be able to give me the depth associated with that duration and frequency of a storm event. And then if I need to adjust that from a point to an area, there's another curve I would have to look at, right? That says, okay, for a storm event of this duration, it's going to actually be 70% of the point depth over a 10 square mile watershed or something like that. I would give you stuff. I would just have you interpret it. Yeah. And I'm going to grade I'm going to give you feedback on the in-class assignment stuff. I graded all the homeworks, but the in-class assignments related to design hydrology and stuff, I'll make sure you've got solutions and stuff to that. All right, see you guys.